Yeah, so today we're very happy to have Tom Hagen from OpenGeoHub Foundation here. So Tom has more than 25 years of experience as an environmental modeler, data scientist, and spatial analyst. So Tom has a background in soil mapping and geoinformation sciences. He has PhD at Washington University, ITC, and he continuously runs hands-on R training courses to promote use of open source softwares for spatial analysis and spatial modeling purposes. He is currently the project leader of the Open Earth Monitor project and director at the Open GeoHub Foundation. So yes, right now, Tom, the floor is yours.
Okay, thank you so much, and thank you for invitation. Let me just have to organize this just a second. You can see my slides, right? Now I turn it off.
Not anymore. They were there, but not full screen.
Let's see. Just have to check if I can project it on Zoom. You see my slides now?
Yes, but it's not full screen still.
Okay. Let's see. Oh, yeah, now it's working.
Yes, good. Thank you.
Yeah. All right. So yes, I'm going to talk about specifically about reconstruction of Landsat archive. I wrote this sun, cloud, snow, noise, and humans. So I will start with talking about this reconstruction of Earth observation data, especially optical data. But then I will switch to modeling, and that's why I mentioned this. I mentioned also this noise in humans, so I will explain you what I mean by that. I hope its title is intriguing enough. So yes, I lead a project called OpenNet Monitor, and it's a project of about 100 people, and it's finishing actually this year. So we produced already about 80%, I think, of things we planned. And one of the things that we produce is Landsat version 1. We also produce some Sentinel, Copernicus Sentinel 2 based products. And we also have about 30 use cases, and we contributed the OpenEO software. So that's what the OpenNet Monitor project is famous about. So I'm going to specifically talk. So this project, the OpenNet Monitor, it's like, as I said, 100 people, and I think it's 23 partners. So there's a lot of things happening, but I'll specifically talk about this building of the cloud-free bi-monthly mosaics. And then we call that version 1. And now we're working on the version 2, which is the monthly. So we go from bi-monthly to monthly. And then I'm also going to talk a bit about the space-time machine learning and how is it different from purely spatial machine learning. And then I'm going to show you with the example of gross dry matter productivity from Copernicus-led monitoring service, how you can use space-time machine learning actually to explain almost 80% of variation in the GDMP just by using latitude. Also, I should mention, we just published in December this extensive report. So if you're interested in OpenNet Monitor, you can read. It's on Zenodo. There is also a policy brief. So that kind of summarizes what we discovered and some interesting things that popped up. Key deliverables, there's many, but this is just a subset. But as you see, we made this, one of the key deliverables, we made this Landsat bi-monthly archive. And then also we made a terrain model, global ensemble terrain model, which is actually now has 15 terrain variables at 6 scales. So 30, 60, 120, 240, 480, and 960 meter. There's also pantropical commodity 10 meter from Sentinel, Copernicus Sentinel. There's a map of drivers of deforestation for Africa. Also synergize, digitize 50 million field boundaries for EU. So there's a lot of things that we contributed, mainly mainly data set. We also organized 4 conferences, and we video recorded all talks. So there's more than 100 videos available. This is a typical example of OpenNet Monitor. We take multiple products. So, for example, this is the ESA world cover, then the world serial, forest data, partnership data, global mangrove watch data, so multi-source data. And we produce a 5-year, 10-meter resolution product, which has actually very extensive number of classes, and it's kind of a mixture between natural vegetation, agriculture, different type of crops. So we produce kind of ensemble product, and we clean it up and we document things. Then
what's the schema for the labeling over there? What was on the right hand side? What was the schema there?
This is the legend of this ensemble product.
Right now, but what's the labeling schema? So is that the UNIS product or?
No, we made a new one, which is based on these 4 products here. So we have a ESA world cover, world serial, then forest data, partnership data, and global mangrove watch, right? And then we made a rule, and then we combine. Now we also work on ensemble and cover, which is based on modeling, so not based on our human rules, but on modeling. Because people, there's too many now land cover products, and often people want simplicity. And one way to get to simplicity is to make ensemble product, which is the best of the best. We were also blessed to get a copy of Landsat. So we collaborated with the Maryland University, with the Matt Hansen group, and they spent, I think, almost a decade producing this, what I call like a harmonized Landsat product, because they apply all this correction, and they use MODIS to correct different Landsat sources from Landsat 5 to Landsat 8 and now Landsat 9. And it's a 16-day. It's a 16-day composites. And we got a copy. So we got a copy on our infrastructure, and this Landsat ARD from Maryland, it's basically in tiles. It's about 19,000 tiles, and 1 year is about 53 terabyte. So now we got the year 2025. We can just download, but the first copy we actually got physical copy on discs. So they sent it to us, and they were very nice. And then we integrated it in our own system. And then when you look at these 16-day products, there something like this thing on the left. It will still be clouds and artifacts, missing things. But what we need actually for applications, we need something like this, the one on the right. So that's what we spend almost 1 year figuring out how to get from this to this. And we did, of course, literature review, and we look at different signal reconstruction approaches, and we noticed that you could do like really modeling and like do a full reconstruction, so you fit a red line through all the values for every band. But then on the end we came up to this framework, because it's really large data. We have our own computing infrastructure, so we don't want to overload it too much. So we came to this infrastructure and approach, which is relatively simple. You remove the clouds and snow and all the issues that you have through quality flag, and then you can derive B monthly values. So if it's a 16-day, so it's about 6 values. You take, for example, mean value, and you can weight it by the cloud cover. It's possible. And once you have this B monthly aggregation, then you have still a lot of gaps. About 30% will be missing values. And then you can do temporal gap filling. And once that's done, you can create mosaics. And because we couldn't handle this data size, we also converted the integer 16 to byte. and we reduce this time steps 16-day to so from 598 16-day steps to 312. So you reduce it significantly. And on the end, you have something which is without gaps. This is an example. These are the true images from this 16-day, different 16-day periods. And we get to, first we get something like this. This is the mean value from 2 months. And then after we have the mean value, we still have some gaps. And then we do this SWA. And so that's a kind of reconstruction functions. Basically, it's a moving weighted filter that you apply through time, and then you get something complete. And at the first instance, we use both the past and the future to do the gap filling. But later on, we discovered that it's nonsensical to use future to reconstruct the past. So we only use it one way on the end. So we use it only from past to future, only one direction. And as you see, these weights, these are weights, actual weights. The weights, they drop exponentially. So they will be exponentially much smaller as you move away in time. And so that's also publication. I think you saw it maybe. It explains this derivation of these global mosaics. And on the end, we produce something like, let me see how many, 156 mosaics. So bi-monthly from 2000 to 2022. Now we have already 2023, 24, and we're just building 25. And that's about 20 terabyte of data. And then when we completed everything, all the bands and everything, then we got about 150 terabyte. So bi-monthly mosaics about 150 terabyte. This is one example of bi-monthly mosaic. It looks pretty good. I think when you zoom in, you can see it's complete consistent, and you don't see any lines or any artifacts. So it just really thanks to this smoothing, finding the right smoothing function and using data from previous months and previous years to fill the gaps. So you visually don't see any like inconsistencies and things. So that was the version 1, but I'm hiding now. Of course, when I present the best example. What I'm hiding is for the winter months for Europe, for the Northern Hemisphere, winter months, so all the way from November, December, January, February, March, we notice there's still a lot of problems. So it's not simple. Even we forgot about it, but in the winter time, in the January, February, December, January, February, you have also polar night. So above some latitude, actually, you don't get any Landsat data. So you have a whole complete gap. And we tried to gap fill it, but it was nonsensical because that part of the planet is simply in the dark. And so we produced this, and we even made this mosaic. We made it just as a 1 geotiff. Usually it's about 150 gigabyte with compression. So it's just a one image. You can drag and drop it in QGIS. It works quite smooth thanks to this COG solution. So many people were excited. I can just drag and drop whole world 30 meter in my QGIS and without a problem. And this data also, as I said, we put it on CDSC, hosted in Poland by Cloudflare. So they made it really available. It's at 130 terabyte. I said 150, but it's 130. And so it's available here in their stack. I don't know if you use the CDSC, but they have almost 80 petabyte of Earth observation data. This is just a small contribution, but officially, if you go to CDSC and you need the data before 2017, the only data which is ready to go is these mosaics that we prepared. So that is still for years before 2017, 2016. The only data you can use is this Landsat bi-monthly mosaics we produced. And as we kind of master this processing of Landsat, we published, I think, something like 10 something publications, very different applications, from land cover mapping, grassland mapping, livestock mapping, to mapping. Here you see median vegetation height. And we got a reasonable accuracy, and I think it's still one of the rare data sets that you have an annual vegetation height with, at every pixel we also have uncertainty. So we have both the predictions and uncertainty. And now we work on the version 2, and we want to switch from bi-monthly to monthly, because we notice that's an issue for many applications, because if you have bi-monthly in summer or spring months, you cannot really do a successful modeling of, let's say, yields and crop types and things. And we will use this time integer 16, so we'll keep the precision as the original. And also we will produce this all the way from 2000 to 2025. So that will be about almost 2,500 mosaics and about half petabyte. So that's the estimate. And we would like, for every pixel now, when we do this gap filling, for every pixel, we would also like to provide information of the accuracy or the quality of the values. So we can have just some quality label, like quality 1, quality 2, quality 3, but we could also provide actually what is the error, estimated error. And now we have a team. We're about 25 people at OpenGeoHub, and also Josip Križan from Croatia. He's also doing a lot of coding, but at the moment, Sajed, he's leading the coding and processing. And we had today meeting, so I will show you some examples. It's already getting exciting. And our estimate is that version 2, if we apply nothing too like sophisticated, but something, lots of things implemented in C++ and running on InfiniBand, our estimate is that we could process the whole world, all 26 years, and produce this cloud-free monthly mosaics within 3 or 4 weeks. So that's the plan. Josip also looked at there was one publication group from Canada actually working with US data. They use this neural net-based closed form continuous algorithm, which is explained in this paper. And these people reported that by using this CFC algorithm, they get much lower errors in extrapolation areas. So they said it looks very promising. And we also tried using that for the whole world. And we optimize it a bit. We use about 54 million training pixels, randomly subset all around the world. And we got a relatively high square, 0.96. And however, this model, it's a full reconstruction. So see, this is the bi-monthly, the bi-monthly product, where you still see some lines and these Landsat scenes. And this one is the CFC-based reconstruction monthly. So here you have one image, here you have 2 images, and you can see it's way smoother, but it's a full reconstruction. So you really fit values through all the pixels. And so the CFC is the blue line. So here, the blue line, that's the reconstruction. So the nice thing about it is that doing a reconstruction, so it means basically you can completely control. You can say, I want the values on the 15th of January, 15th of February, 15th of March. So you have a full control of the regularity. But disadvantage is very computational. So you have to really repredict everything, all the pixels for all the bands. And so we tried that and we said, yeah, this is not going to work. And then also when we zoom in, so you see here on the left side is the CFC output. There's still some patterns which are a bit kind of some artifacts or issues. So we still see some issues, even though it's fitted curves. So for imagine every pixel is like a time series, and you fit like curves through every pixel time series. So this is the beginning of the time, so 2024. And so you basically feel like, trillions of models. And then when you predict also, you expect to have something smoother, but it still has some issues. And so now we are switching to something which we think it's less computational, and something because we don't think it has to be so complicated. And I will show you the results we get now, because we think problem with Landsat is that the many artifacts, there are not many artifacts in the images, like some lines and ends of scenes, and also there's some artifacts in the Landsat 5 because of the scanner limitations. So we noticed that actually what's more important than this modeling, more important is to do really careful removal of artifacts. And artifacts can be only about like 2 to 3% of the whole pixels of the world. But if you use them to smooth, if you use them to take mean value, they propagate all around. So they really spill out, And so that's why we are doing something now more simple, but more aggressive towards removing artifacts. So we are, for example, we derive this long-term monthly values for all the bands. I can show you that now very quickly. I'll show you the actual data. So let me see. So here's an example. If you see my QGIS session, this is I think Venice, and this is near infrared band. And as you see, it's really almost perfect because this is the month November. Sorry, this is month November, and you can see it's really almost no artifacts. It's very smooth. And you can see seasonality changes from one month to the other. So it's very consistent, and no serious artifacts being propagated. But this is that's the median value from 26 years of March data. So you take all Marches for 26 years, and you can derive any quantile you wish, of course. We derive the interquantile range, median, and standard deviation. And once we do that, we see that it is very smooth. So it's a very, very efficient way to remove artifacts and to estimate distribution per pixel. We also have land cover classes for all the 26 years. We even have a fraction of, so we call indicator classes, so we know how much tree cover, etc. And so we can really cross-check, and we can look at these distributions of signal, and we can also, for every pixel, we can see what will be potential outliers. For example, if you use 3 standard deviations, if you have a median value and 3 standard deviations, you can check any pixel, any value. You can check whether it's artifact, it's some real event. And so that's going now so very well. So now we will use this distribution to more efficiently filter the artifacts. And we think that's going to help us significantly because if you remove the artifacts efficiently, then they will not spill, they will not propagate, and then the gap filling also becomes easier. And so we're doing this 4-step framework where we will first derive these long-term distributions for every pixel for every band. So that's 12 images per band for 26 years. And then we will derive monthly median, specifically for a year month, and significantly reduce these effects of cloud, snow, and noise. And then we will do first soft gap filling with a convolutional filter and using consistent land cover classes. So if you go backward, for example, 3 years, and you say last 3 years the land cover is the same, so it's the same class, then you use the 3 years. But if there's a change in land cover, then you stop using, because you don't want to propagate values for different land cover. And then in the last phase, we will do gap filling using modeling. So we hope to reduce slowly number of clouds and artifacts to only about 20%. That's our hope. We still have to test it, but let's say 20 to 30%. And then these remaining things we can do with modeling. And for modeling, we are looking at fitting a single model, which is the space-time model for all bands. So I will show you that we already tested it, so it's possible. You build a single model for all space-time Landsat, and for multi-response model for 7 bands, and then you can predict anywhere in space-time. So you just have to say this is the latitude, longitude, day of the year, and you can use also some covariate layers. And so I know you are working on Tessera, so congratulations on that. We would like to plug in, I just made today an email I wrote, we would like to plug in your Tessera into our biggest project that we want to call Open Geospatial Carbon Registry, OGCR. We would like to plug it in and make it official data source for assessment of carbon fluxes across Europe at 10 meter. Zheng Peng is helping me. So hopefully we get that in our infrastructure, and then we can make above ground biomass and soil organic carbon for whole Europe at 10 meter with uncertainty per pixel. And so that's very exciting. And I know that you just recently improved the Tessera, and now it's a bit more complete. Although we would also like Turkey, if possible. I don't know when you will have it, but we do also put Turkey as in our map of Europe, and also we put Iceland. So there's a little piece, but it's not a problem. This OGCR project is next 3 years, so we still have 3 years, and next year we have to actually, or end of this year, we have to have a prototype. Next year we have to deliver above ground biomass annual and soil organic carbon annual with the prediction intervals per pixel. And so we are excited to use that, and that's independent from this Landsat, but it will be also interesting to, I don't know if we should use for that original Landsat, the 16-day with the clouds, or we could derive this monthly Landsat for the bands, and then fit embeddings, fit a model for embeddings for Landsat for 2025. That will be also very interesting if we could do something together, maybe. But we are totally open to working with that. So very quickly about spatial temporal machine learning. So spatial temporal machine learning it's a bit extension of spatial modeling. The difference is you overlay in space-time. Obviously, you match points in space and time. Usually work with time series data. Then there's also special, what we call temporal covariates, which can be also cumulative covariates. And then also it's very important when you do space-time machine learning, you have to do this blocking to cross-validate both in space and time, because if you ignore that some things are repeated in time, that you can overfit. So these are special things about spatial temporal machine learning. And usually, as I said, we organize the data as a data cube, and then we can do a space-time overlay. which means we can match somebody on the ground doing some in situ observations. You can match exactly the month or the day of the year and the year, and then you look for the values of the covariates in the space-time data cubes. And then you build a model, and then you can apply that model to predict. Then, as I said, you can also use cumulative variables. So this is annual precipitation. So you can take multiple years, and then you produce new set of covariates which are accumulated precipitation. So it's always growing, but seasonally. And you can also use these cumulative variables in the space-time machine learning, and they help you represent this long-term influence of climate. You can also take derivatives of cumulative. So you can put actually many tens of new covariates, because when you work with space-time, there's a lot of things that it's, you can put all this first. So the cumulative values, first derivative, second derivative, etc. So one variable like a rainfall, it can be turned into like tens of variables, and you can all plug them in the machine learning. So I played a bit with the gross dry matter productivity, which is derived from satellite images often, either as GPP or GDMP. So I looked a bit like if you model this GDMP using space-time model, how did this model look like? I was just exploring. And that's why I want to show you that actually I was actually surprised how systematic is, especially vegetation variation. It's very systematic, it's very seasonal, etc. So I took this dry matter productivity from Land Copernicus CLMS, Copernicus Land Monitoring Services. It's available from 2014 to today. It's relatively coarse resolution. I was still testing things. It's about 300 meter. I looked at the problem first conceptually. So I said monthly variation is probably the most important. So seasonal variation is the 4 stars. So that's the most important. And this one depends on the latitude and day of the year. You could say there's also impact of interannual variability, like some El Nino, La Nina effects on the GDMP, maybe some dry years, wet years, etc. And there's also some long-term trends. And the daytime, nighttime, at the moment I ignore effect on the GDMP, although you know that, of course, during the daytime you have a much higher GDMP. So we wanted a simple algorithm, and we wanted something that we can use to fit in the gaps. And we want something which is for the whole space-time cube. So a single model, and as much as possible based on some theory. So when I said something like this, so it's a design to match what we know about that feature. And we do have a paper also explaining this type of modeling, but not using the CLMS. We use the MODIS FAPA. So it's a very similar approach. And we created a sampling design, which is based on equal area projection. And it's a stratified optimized sampling. So you have, basically you see points are kind of spread over all continents, all climate zones. But some areas we have a bit lower density. And so we created that, and you can see now when you overlay, so one location, multiple months. So we're talking monthly values. You can see this is the precipitation, temperature, and GDMP. And you can see they're kind of synchronized. There is sometimes a bit of delay. So first you have a bit of rainfall. So here's the rainfall starts before the growth of the GDMP. So there's a bit of delay, but it's kind of very synchronized. And you can see when there's a 1 year, you see this year there's a precipitation a bit less, and you see it has the effect on the GDMP. So it looks like it's a very highly correlated. And then I add this geometric temperature. I don't know if you ever heard of geometric temperature, but it's basically it's a function that translates latitude, day of the year, and you can also put elevation. And it looks something like this. So it shows you this seasonality. So you can compute it on the fly for any day, any latitude. Longitude doesn't count, right? It's just a latitude, the day of the year. But because we also plug in the elevation, there's this elevation gradient. I think every 100 meter, the temperature drops 0.6 degrees. So when you plug it in, then you also need a longitude. So you have a very elegant way to translate latitude, longitude, and day of the year and elevation. You translate it into a covariate, which is now on sphere geometry covariate. But it has this is no Earth observation data. This is purely that's why it's called geometric temperature. It's purely based on the sphere geometry. The only thing we use is the elevation actually as a geographical data. But let's say elevation is static. I mean, that doesn't change. So when you compute this, you have to compute it only once, and then you can use it for multiple years. Then I also wanted to do the same thing for precipitation, because global precipitation is also very systematic. So you could represent it with mathematical function, but I don't have it yet. We started working on it, because it's a precipitation as a function of these masses, density of masses and things. And it also here around the equator, it has a peak. So it's also quite systematic, but we don't have a mathematical function. But it will be possible probably to represent that. And then we looked at this also plugging in a land cover, which is also inexpensive, very simple. And we looked at that. If you take the land cover, then this GDMP, it does really change. For example, for bare areas, much lower than if you compare it to forest or the grassland. So you have but in general expectations, the curve should look something like this. So that's the curve if you go in months. So that's a usual what the literature shows. So it's a very seasonal. And this is so just taking GDMP space-time as a function of geometric temperature, land cover, water vapor precipitation, which is just atmospheric products, you get a model which explains 0.8, 80% of variation in the GDMP. It's amazing. So just by using like some sphere geometry, so that was really a discovery for us. And we think with this type of models, so relatively simple model, not over parameterized, and also models that don't use any Earth observation data. So it only uses the atmospheric products like precipitation, etc., and water vapor. With this model, we can explain a lot of seasonality in vegetation, and that's why we want to use a model like this. We would like to use it to gap fill Landsat bands. So that's the last step, as I showed you. And we tested also this model versus the actual measurements on the ground using FluxNet and eddy covariance flux towers, and also it matches. So this accuracy we get it also very similar on the actual data. So in summary, the problem with using, of course, Earth observation data is that we have only snapshots of in optical sensing. There's only snapshots of the landscape, vegetation. So to get something more usable, so you can really run time series analysis, something which is seamless, you need to do this reconstruction, or you need to do like really serious aggregation. Aggregation really works if you do it properly, and if you have it a lot of years. Now we have 26 high quality years, even more, almost 30 years of Landsat. Doing that aggregation allows you to like really see a very smooth a view of that of the landscape, and you can use that distributions, then long-term distributions, to filter out artifacts and all these problems with the Landsat. And we are now working on this version 2, and it's going to be run using this 4-step process, and we hope to have it somewhere before summer. We're going to release it, and it will be about 0.5 petabyte, and we're very excited. We think that could really enable lots of people. It will be distributed as open data, and we think this could really enable a lot of people to do like a long-term analysis, especially to analyze ecosystem health, soil health, land degradation, etc. And we are also planning a publication, of course, and we would like to combine forces with you to potentially derive embeddings from 2025 or even 26 next year. We would like to derive annual embeddings, which are based on Landsat and terrain variables and possibly MODIS. And just to mention, we are hosting a conference in Barcelona. Most welcome to come. One of your colleagues is a keynote at this conference, so it's in October. Most welcome to come. I'm also in UK in June. I'm invited as a keynote at the ML4EO. I don't know if you're familiar with your colleagues.
It's in Exeter.
Yes, Exeter. Yeah. So I will be there in June. I could maybe come and visit you in Cambridge if it's on the way. We have a summer school in Istanbul. We already got almost 200 applications for summer school, but we can only host, I think, 120 people. So now we have to select. So the application is already closed, but we're also very excited to come to Istanbul, and it's a summer school on EO data science. So the data science specialized in Earth observation data. Last summer school, it's been video recorded. All our events are video recorded in high quality, and you can watch both on YouTube and on the German channel TAB. You can watch all the talks, and there's a very interesting things. Also, a lot of interesting talks about Sentinel-1, and there's also discussion panels video recorded. So it's almost 40 videos every event we organize. And with this thing, I stop my presentation. I hope there's still some time if you have questions.
Great, thank you very much. Yeah, we have that question. Anybody in the room?
Thank you for the talk. I have a question. When you talk about interpolating Landsat images, how do you deal? Can you go into a little bit more details on how do you deal with disturbances or actual changes in land cover when you try to interpolate over that period?
Yes, that's the thing we learn a lot. I think in the version 1 of the Landsat. So we really learn a lot, and we noticed, for example, that in version 1 actually we ignore the land cover changes. So we don't use any land cover information. In the version 2, we actually have for every year we have a ensemble land cover. So land cover which is based on multiple products, and we took a simplified one with 11 classes. So we have a land cover from 2000 to 2025. And so now when we do this step, the step number 3, we're going to apply it only where the land cover is consistent. So there's no change in land cover. So it has to be land cover consistent. And I think this is going to help because if you have like a clear cut of the forest, if you have a fire, if you have a flood, if you have a sudden urbanization, then if you interpolate in time, I totally agree. You kind of smooth out, or you spill some event which is artificial then. But it's very funny. Like when I show you this, when I show people this image, they are actually really surprised how good it is. There's really very little, but this is only visually. Visually, it looks like oh my God, it's so perfect. It's like it's smooth. There's no lines, nothing. But this is only visually. Actually, when you look at about maybe few percent of the planet, or maybe 5% of the planet, if you really carefully look, then for some years we propagate this, we smooth out between years, and it's incorrect because there is a sudden change in land cover. And so now in version 2, we want to deal with that. So we're going to apply this method, and we are going to use consistently land cover classes. So we will only interpolate in time where there's no land cover change.
Yeah, because if you're interpolating temporally and including post-disturbance states, then you can also have the disturbance leak to the previous
Yes,
time steps as
no,
well.
I
So
saw
we're
it.
trying to, and it's smooth.
I
Yeah,
saw
and
it
just
in Brazil. In Brazil, because in Brazil there's a really rapid, especially last 25 years, really rapid change of land cover, right? And we saw it at how it's almost like the future propagates into past, and it's completely wrong, right? Because future. I mean, in the sci-fi movies, somebody travels from future to the past. But the future there's no causality. I mean, the causality works only one way, you know, only the past should impact the future pixels. So we noticed it was a serious. So version 1 still has these issues, and that's why we work on version 2. And fingers crossed that we will significantly reduce. At least we will guarantee that the land cover is consistent, and we will use the best land cover, which is the ensemble land cover. And so we are hoping it's going to work.
and ensemble is just from the existing global land cover products.
Yes, we take a three global 30-meter resolution products, so we build a one consistent land cover. We use the Maryland University GLAD land cover, and then we use the Chinese land cover, and we combine with the SSCCI land cover. So there's a three land cover products, and we integrate them.
Thank you.
Thank you.
Any other? So I had a question about so what's the repeat frequency of the Landsat satellite? Is it every 16 days? What is the often?
So original Landsat, you know, it's like a change from mission to mission, right? It changed a bit, and that was a problem. And that's why the colleagues in University of Maryland, they created this 16-day. So they take this best pixel. They don't do any smoothing, you know, there's no smoothing, there's no, so they take the best pixel. But because you have Landsat 5, Landsat 7, Landsat 8, and they are they are supposed to be harmonized, but actually they're different sensors. So they did this, they did a kind of correction, this one, reflectance normalization. So they apply this using MODIS, because MODIS is consistent. Landsat is not consistent. They apply this correction, and they produce this kind of harmonized Landsat. So they keep the pixels, basically they take the best pixel, but then they adjust the value of the pixel using the MODIS 44C product. And then you have all the, because, you know, it's no joke. There's no joke. I mean, there is a serious issue if you want to use this time series data. And if you say, I'm looking at, for example, some gentle degradation or loss of the density of trees or soil erosion or something like this, then you need to have harmonized product, because the changes in biomass or soil or whatever could be factor of having different sensors, different satellites. That's very dangerous, because somebody will say, hey, here there's a change, but you say, but actually part of the change is because there's a different sensor, you know, and that's why the GLAD says, no, we need to remove that. So they apply this reflectance normalization, and they still maintain this 16-day. Now I heard that USGS, I think they also want to maintain it. But I'm not sure now what's happening in US, to be honest. But they still produce they produce the 2025. They will produce probably also 2026. So they still produce that, and it's also again very big, you know. And you have still clouds and everything. So now it's about 1.5 petabyte. So it's not something that you can easily process. But when we produce this version 2. It will be monthly, so it's not a 16-day. It's a monthly, but it will be consistent, complete, and you know, no artifacts, etc. So that's the things I was showing you in QGIS. And
the reason I'm asking this, thank you very much. That is really a very interesting to know. That's the question was, in terms of the monthly signal, do you feel that that retains the phenology properties of the underlying system if you do it once per month? Because, like if you talk about crops, you basically have no signal between October and March in the northern hemisphere, above, let's say, 30 degrees. So you only have like 6 data points you're going to get, or 7 data points between March and October, and that's so. Is that sufficient for us to determine phenological properties such as crop type or canopy height, things like that?
So if you look at so I need to explain you this scheme. I have to actually make something visual. I think it's difficult to. So like the first value derived is this median value, so it's smoothed, and we use median because usually the clouds are high values, and they can have a high impact. So if you take a mean, it will propagate this impact of haze and things. But if you take a median, then you remove that effect. Then the next step is what we call naive gap filling. This step 3, and here you look for the consistent land cover, and you can go back in time, and you can go 1 year, 2 years, 3 years. So often you get lucky. So for every pixel, the clouds go around. They're not always the same, except for like Indonesia and parts of Brazil, Amazon, you have clouds really non-stop. And so that's a problem. That's not easy. But then you really have to do this modeling. So we really have to gap fill with the modeling. But otherwise, you can. We estimated that we can just by going like 1 or 2 years back, we can find lots of pixels still. So about 60% of gaps we can fill in with this very cheap method. And as long as it's a consistent land cover, it's not a big, I would say it's not a big, the error of gap filling, it's not big, and we tested it, so it's a very small error for consistent land cover. If you had an inconsistent land cover, then probably you are mixing things and the errors have become high. But if you do it consistent, then the errors will be small. And then the last round is the gap filling things that you cannot find values like previous year or year before. You cannot find any values. Then you do really have to do modeling to gap fill it. That's the only way, the only way. Everything else is like what I was showing you in this. I'll share it one more time. So here's this screen I had, this one. So here you can see I take one. This is just one tile, and I take 26 years, and I take the median. So I have everything. But if I zoom in, even in 26 years, there's no pixels here, because this is industry, and it has always like it can be like sun rays, reflect or something. And it's always it's always some artifact, and that's a problem, because we don't have any pixels. There's no way I can gap fill it with this 26 years of data. So I need to do some modeling. I need to put a model. I need to really just gap fill it, but it's only like 1%, 2% of pixels. So I don't. It's a harm, Like sometimes you have to find a balance, in data science. You don't have the perfect data, but you rather gap fill this, 1 or 2% with some model which is, it has an error, but you rather have something than nothing, right? As long as the model, you can show that it's consistent.
Thank you very much. Are there any other questions in the room or online? If you're online, you have a question. Yeah, go ahead. Yeah.
Thank you for the talk, Tom. I was just wondering, do you think embeddings like from Tessera can help you do some of these gap fillings instead of land cover maps? You can have pixels that are changed.
Yes, that's an excellent question. So there is for the years from 2017 to 2025, 26, you could actually just use embeddings, and you can reconstruct. You could fit the model to reconstruct, for example, Landsat, and it will be probably better than if you just use Landsat data, because your embeddings are based on Sentinel. It's a high quality, high resolution, but this is only from 2017, right? So the question is, can you use embeddings, Tessera embeddings for our projects? And we would like to actually move even further back. We would like to move to 1997. We would like to have from 1997 to 2027. It's a very nice round number. It's 30 years. And if you have 30 years, you can really show, look, there is an effect of global warming. There's an effect on landscape. There's for example, soil erosion happens on a scale of like 5-10 years. So you can really quantify these slower processes that are a bit hidden. And so we are hoping to have 30 years. So the question is, can Tessera embeddings help us with 30 years reconstruction? My answer is probably no. It can only help from 2017. So that's always a problem that Europeans, unfortunately, European Space Agency came very, very late in the Earth observation space. When you think about it, the first 30-meter images are from 1985, and European Space Agency started doing operational stuff and has images from I think they start 2014, but nobody uses before 2016, right? So there is a huge gap there. But it will be interesting to make a product on like, I mean, I guess you will refit your Tessera. Probably you will have better ideas. And I always tell people, because we made these global terrain variables, so you have like catchment area, openness, morphometry of terrain from slope to curvatures. So it's about 15 of these variables, and they're at 30 meter. So I said, why don't you incorporate them into embeddings? I mean, they're open data. They're based also on the best possible data. So, and also you could put in embeddings potentially geomorphological units and lithological information, you know? And so then now the embeddings are purely based on Sentinel 1 and 2, if I understand right. But it would be nice to incorporate this detailed information about terrain complexity, and that will be interesting to see, because there's an overlap, you know. There's an overlap if you know the area.
Yeah, thank you very much. And we did actually consider that, and the decision we came to was to make that a downstream task decision, whether to use additional climatic variables or terrain variables for the task at hand, rather than keeping the embedding itself pretty purely based on Sentinel 1 and 2. But I mean, that's one could argue that's whether it's the right decision or not. I'm afraid we have run out of time, so let's thank Tom once again. And
nice to see everyone. Hope to see you in person soon, whether in Exeter or in Cambridge. I look forward to collaborating with you. Good luck with your work. Bye bye.